It's really a pleasure to be part of this event. And okay, I'm just starting. So about me, a lot of people commented that I've written C Commodore 64 programmer. That's how I started. It still sticks to my mind. A lot of Commodore details that I don't really need, but they are there. Somewhere later, I switched to Amiga, and for a couple of years, I was C and C++ programmer. Then that really took a long time. I'm now 20 years with Java JVM. In the meantime, I learned JavaScript, which was painful, and Scala, luckily, and Kotlin. Recently, in fact, I program mostly in Kotlin, but Scala is still close to my heart. Okay, so the motivation for this talk is actually something that I have always in mind, and it's from my experience. Like mythical slow solution. I'm not sure if everyone of you had this before and knows what I am talking about, but probably you've seen such statements. And you even believe in such statements because, yeah, basic is slow. That's the first thing I've learned, and I actually experienced that. Basic on Commodore was a slow thing. And then while I switched to assembly, which no one was saying it's really slow, but people were telling that, oh, C language is slow, which now sounds funny. Yeah. And then I learned, that doing post-decrementation I have to be careful because pre-decrementation is actually faster. Really, like 20 years ago, there were still such statements. And then I learned that collections are slow, that Java is obviously slow, I don't know, and I still remember it was really slow. And object-oriented programming is obviously slow, but it's nothing compared to functional programming. And it all is really nothing when we look at monad transformers, obviously. Yeah, that's what we hear. And of course, it's not that it's not true. Some of these things, and maybe most of them, are actually, they make sense. They come from some experience, of course. But is it always true? Is it true in each context? That's the thing. And that is the content, that's my talk about. So first, long time ago, I was writing in assembly, and then I had the first moment in my life when I was really thinking about something. So this is a Commodore assembly, and there is like instruction. Some of you might know it. Conditional branch. What was really important at that time, the cycle on Commodore, each cycle was important. You wouldn't waste a cycle, and sometimes it's not even because of being fast, but not to miss the very exact moment. You had to be really precise. Conditional branch on assembly at that time had this particular feature that if you really jumped, it was taking 3 cycles, and if not, you were taking 2 cycles. Of course, okay, no. Actually obvious, if you really do jump, not only just test condition, it must be longer. Yeah. The point is that if you look at some if statements, we're really carefully writing them in order to save this cycle. So for instance, if it was possible to change if to negation and a little bit logic just to make that in most of cases you wouldn't jump but go through, and the else case, the jump would be like something uncommon, then you would do that in order to save a cycle, obviously. And yeah, that's what I did later also on Amiga. By the way, it was really hard. And mostly it wasn't needed, especially on Amiga. But then I learned something funny. Beginning of 90s, Motorola introduced a new processor, 60840. And this processor had one particular interesting thing, that taken branch was faster than not taken, because they changed the prediction strategy. How do they take thing from the, let's say, order of Q? That they analyzed, Motorola analyzed that actually, no matter what we, like, let's say, hackers are trying to do, most of the branches are taken. It's like ratio 90 to 10. So they implemented a strategy that actually branch taken was faster. Now, you should understand our pain, that for years we've been doing something that now works against performance, actually, even though it was something obviously that, yeah, we take this, took this branch strategy as something that will never change, obviously. Yeah, that was a hard lesson. By the way, I never had this processor. Nevertheless, it was for me funny feeling that I did something actually against the users in order to make something faster and better. Yeah. So Motorola behaved for us like a little bit of troll, but that's where I learned about, premature optimization being a root of all evil. And all of us heard about this. This is nothing really special. Yeah, we also know that we shouldn't do prematurely optimizations. Yeah, but nevertheless, we still have these performance myths about something. Those myths are the statements we believe we have in our heads. The statements that somehow really come from the truth, come from the experience, but in fact are not really precise. They are too generic. They are sometimes valid only in certain contexts, basically the same. And sometimes they were only valid in the past. Sometimes are just not relevant at all for our code, for our business context. So that's the problem. And of course, this problem leads to a lot of to some cost. We create code that is just less maintainable. And something that is hard to measure, but I think a lot of our developers, we just lose a focus. We talk about things that are not really relevant because in one moment, someone will say, I will just use here a monad, and someone will say, oh, and it will all be too slow. And then we start talking about something completely indifferent to our business goal. Even though, yeah, we'll see. So why is that? Because I believe partially, okay, this is not something I really believe. I read it in the books that we humans like numbers. So when we present something, we want to market something, it's best to present some numbers. Which numbers can you present? Can you present number that shows like your code will be 60% cleaner? Like 20% more maintainable, like testable. It's hard. On the other hand, making a simple benchmark, no matter how broken, but it's very easy to present some numbers, especially that show that your library is just so much awesome and beats everything else. So Scala, that's, by the way, happens in every language that I know. It's no matter if it's like Java or even Python or something that we don't associate with performance sometimes. And Scala, is high-level language, functional. Is it maybe immune to the problem? Like, because, Scala is far from metal, okay, which is actually sounds funny when someone uses metals, but, we are very high level. So the point is that if we go to the Google, if we go to the conference, listen to talks, we see that it's the same story again. Like, claims that this is high performant, this is less performant. And again, I don't say this is, no, it's actually very awesome that we have such talks. Those are, let's say, for me, very interesting statements that I really love to see, to hear, to analyze. But I think then as a developers, we spend too much time actually being defocused on what we've heard. Because most of the time, even if that was the truth, it's not irrelevant for us. The problem with performance in Scala is also that it's not a very easy task for Scala. It's like we have a code in Scala, then we have bytecode compiled by the Scala C. Then we have JVM that runs this bytecode, and JVM is a very complex machine. Inside of this, we have a complicated runtime with garbage collector and stuff like that. But then this bytecode by the JVM is compiled to assembly first, is interpreted. Then it's by various just-in-time compilers compiled to the assembly, to the fast ones. And finally, it's executed on the CPU. The problem is this CPU that we have now in the modern computers is far from this devices we had in the past. And for instance, I'm still thinking in the categories of the CPUs like I learned when I was young. that were completely predictable, that were like easy pieces of code, cycle exact. I knew what is happening there. Not anymore, actually, on the new Intel. It's like, it's, I would say CPU is now almost as, if you go into the details, as complex as JVM itself. And then on top of that, we have Docker's operating system, virtual machines, which what makes the result of that is making any exact statement about performance of the piece of code is basically futile. We'll have a piece of code that we analyze, but putting it in a different context, even making the part of a different project, will make that it will perform differently. This is really not a nice feature of anything that's running on a JVM, but slowly almost of every language. Yeah, the same is for Haskell, actually, with runtime system, laziness. And even with a complex processors, now it's even hard sometimes to say something about C code, the performance of the code. So in this talk, I will present you some benchmarks, some numbers, some things to think about, but I'm actually going to present you the tools. Do not believe my benchmarks. That's what I would like you to do. Don't trust them at all. Think about the tools I will show you. So let's talk about immutability, because I think that everyone, okay, everyone, maybe not everyone, but a lot of developers believe in simple truth. Immutability costs. We create a lot of additional objects, and it's obviously slower than the mutable code. So here, what I have, it's inspired on one of the talks I found about Scala. Let's have an immutable calculator. They done with a case class. This is a very simple one. So we have add method, which creates a copy of calculator with just incremented accumulator, which is here called total. That's it. Then we have a get method to just get the result. Nothing very complex here. To compare it with something, we have a mutable calculator, which is, we have variable. Oh, how ugly is that? And we have just method add, which returns unit. Oh, I'm almost crying, and just modifies this total. That's it. As mutable as it can be. Now, let's analyze what is actually Scala doing of that when you go into the bytecode. So, you know that Scala at the end creates classes, class files. Oh, here is a. So we can read those classes, and basically the easiest thing you can do now with any new modern IDE, you can read those classes as Java. This is just a piece of the code that shows what happened with immutable calculator. What we see here is that there is no magic. The method add calls the copy. This copy somewhere creates new object. Yeah, as we expected, it's really bad. The Scala compiler was not smart here. Didn't make anything, let's say, better. It's really creates a new object, and it's, yeah, I think we'll have to pay the cost. So, by the way, if you don't like IDE, we can really go to the bytecode. For instance, in every JDK, you will find a tool called JavaP, which will then you pass a class and you get this. So this is the add method, and I don't want to spend time about analyzing the bytecode here, but it's very easy language at the end. You can easily read how it behaves, and it's easy to actually follow and to trace what's happening inside of the method. Stack-based, yeah, nothing. That's one of the simplest assembly languages you can find. And assembly, by the way, is simple. It's just not very concise. Yeah. So, but again, in this bytecode, you will see that it's not smart. And by the way, I would say never normal life, no one really needs to read bytecode. This Java code created from class files is way more easy to read, and you won't find anything extra in a bytecode. Although the class files, in fact, contain some additional pieces of information, metadata, and sometimes those are important, but I won't cover this today. This is relevant if you are doing compiler on your own. Okay, maybe once we have a code, we can run it. So Here I have a main method where I am doing two loops here, for like external loop and then internal, where I will just actually 1,000 times call add method just to see some result. And so I want to see how just-in-time compilation works. One way of doing that is using this flag for a JVM. Basically, each JVM understands this flag. And you will then see something like that. In this moment, 6 bytes of assembly was created from this method, etc., etc. So this is a very small piece of the output that you would normally get. It's typically huge. Maybe some hints for you, because some of you have seen that, a lot of people have seen that actually. Numbers here basically show, this column is quite important, shows which compiler was compiling this. So more or less a rule, the higher the number, the more aggressive, more sophisticated compiler. So initially they are all called with 1, let's say client compiler in the past, then 2, 3. This is described, depends on a JVM that you have, and it's there are pages which describe exactly that. That's something interesting, this percent here, it happens a lot. It means that normally the JVM compiles whole methods, but sometimes it says, okay, your method is a little bit long and I am here in a loop. So it compiles a part of the method, piece of code, and it's then you have to do something called on stack replacements. It's actually even more complex, but basically you will see something like that. Sometimes this actually indicates a problem, but that was mostly in the past. Right now it typically works. So by the way, interesting here, my made not entrant, it means that this method was before compiled with a level 3. Now we have level 4. So level 3 was basically marked as not used anymore. Can be collected. There are explanations to that. And OK. You can also see something which is very particularly interesting for JVM, inlining. So that's really one of the best features of JVM, of Hotspot. Actually, it was also I think in the first version 1.3 of Java, and it was for that at that time something really crazy for me. JVM is able to inline even methods that are, let's say, virtual, polymorphic, and from a JVM point of view, and that's still true. And that's one of the most important pieces that features of JVM that make it actually good enough at speed and usable. Inline as much as possible. So you can dump this information, what was inlined. And there are some interesting also heuristics which decide when method is too long to be inlined, etc. And also some additional flags that you can override this. So you can experiment with that and see how much was inlined or not. OK, why do I even bother with that? Because whenever I'm doing some very, let's say, important benchmark, the thing is to check that it was in fact JITed, that it was in fact compiled, that the code you are measuring was really used heavily enough for JVM to be relevant for compilation, or that nothing wrong happened. Right now, I would say I don't see often the problems with the code, but in the past it happened that, for instance, bytecode of a method was too complex, something was miscompiled, for instance, due to code obfuscation in an external library. There were also other things, and basically the method was in fact interpreted, not compiled. There is a thing called uncommon trap. It means basically that JVM is sometimes too aggressive. It compiles code and it says, for instance, you are doing null checking, and even though the object actually statistically is never null, so then it removes this null check. But what if after a couple of thousands of runs, it is a null? Then you will get kind of exception, and method will be rolled back to interpret it, and you will such things. Those are tricks you can even use because it's quite predictable. You can, for instance, create code that behaves incredibly wrong during the benchmark, just because you put some if statement that after, I don't know, 20,000 runs, you change some important Boolean value. And everything fails and everything becomes slow. So, but it's, let's say 15 years ago, that was more important. Right now, it's not. So that's the thing that if you have some real productive server and you can from time to time check what's really compiled if you are analyzing a piece of code and, for instance, see that something is wrong there. But actually, the real tool you want to go for is JMH, Java Micro-Benchmark Harness. So this is like a framework, actually, which takes care about few important things like JVM warm-up and dead code elimination. It's not actually always doing that automatically, let's say. It's you should read description, what to do, and then you might use it. So first, go to the, if you want to use JMH, read, there is a guide that will help you. And JMH is written for Java, a guide is for Java, but you will understand what to do with Scala. And there is a Scala plugin, great Scala plugin for that, which makes it easy to use JMH in Scala with SBT. So I won't cover everything. You are smart enough to do it on your own, but for instance, that's how you make a benchmark, just annotation in some method, and then you can run it. Here I'm presenting something which is called dead code elimination. Basically, in certain JVMs, not everything, not everyone, you might see this problem that if you do some measuring, for instance, logarithm from mathematical logarithm, and you don't return this result, then this method will be incredibly fast, under a nanosecond, which basically means nothing was really happening there. So in order to avoid the trap, if you calculate something, you should always pass this result, and easy for JMH, the easy way to do that is just to return it, JMH in Scala. So there is a special way to call it. I won't really cover that. So basically, if you don't return the result, you might, it's as if you were calling the empty method, or even less, actually. So now we have a tool, so we can use it. Let's measure this calculator, cost of this immutability. So we have two benchmarks. I have somewhere like number of operations, and I will be basically doing mutable calculator addition and immutable calculator addition. Those methods are more or less the same, although not entirely the same, but the difference is basically I want to see the cost of real immutability, creating objects, etc. So let's once again show this and see the numbers. So this is taken and JDK 1.8 from Oracle, yeah, over in JDK actually, this time. And our first result shows that it is really bad for immutable style. So mutable and basic imperative style is so much better than immutable. Like it doesn't even compare. Okay, seems that the common myth is actually totally true. So what can we do? We can maybe hope that the newest Java makes it better. As you see, it is. Still, the numbers are, well, there is a huge difference. But if you see the difference between 15,000 and 3,600, there is something. So by the way, still my numbers were taken unprofessionally. Don't take it too seriously. But it's repetitive. You should see more or less the same results if you do it on your own, and you should. So, but still imperative is better. Okay? Seems that immutability costs a lot still. Unless we try it on the Graal VM. So this is Graal for Java 11, and it's now becomes interesting. If you look carefully, actually imperative, let's say mutable code became a little bit slower compared to the previous example, but immutable code now it's almost on par. It's like maybe 30% slower. This is something that lots of people observed with a Graal, that somehow it magically makes such functional code in some circumstances way better than it was before. By the way, We are talking about the micro benchmark. We don't have much real code here. This is sophisticated example. So this is artificial example. So in reality, it's not that great, but it's still there are observable. Let's say there is observable difference for which makes actually functional code better on a graal. Yeah, a lot of people report that. So, but you know, when we see such benchmarks, we shouldn't just happily go and say, oh, now we'll run everything on a graal. Because maybe it's good to understand what's actually happening in the graal, that it's so much better for this piece of code. And we have some tools for that. So there is an interesting tool, which I recommend you to check if you haven't seen it before. Java Flight Recorder and Java Mission Control. By the way, two names everyone thinks about one tool. What is? Java Flight Recorder is, let's say, just the event recorder that runs inside your JVM. If you have JVM from Oracle, OpenJDK, some of them have it. Not every vendor has Java Flight Recorder. And so let's say this is active part runs with your code. And Java Mission Control is a graphical tool that lets you analyze the recorded events later. So you typically use both, of course. One thing you should know about it, that this is a commercial feature of the JVM of Oracle. However, it's clearly stated that if you use it for evaluation, if you use it on your laptops, you can use it for free. You cannot simply use Java Flight Recorder on a production server for commercial purposes. That's it. By the way, this license was changing, and it's like, let's say, the thing about the flight recorder that you should be always careful about and check how it's now, because in the past there were a lot of misunderstandings and problems about it. I think Oracle didn't know what to do with that actually. So it's not very problematic to turn flight recorder on, and you can find it. You simply record the file, and then you can check what's going on. So I ran this calculator for JVM8, and what I've seen is something you would have with every profiler. So method profiling, you see so many times I've seen this method on a Java 8, etc. And then there are more graphs like showing garbage collection. And some of you see that it's everything, in fact, in every profiler. Yes, indeed. And even I would say profilers like JProfiler are better for that. And even Visual VM sometimes is better for profiling. So free one. But I present a flight recorder because it's not commonly known. So something for you to check. The very important piece about flight recorder is that it's actually designed to run on your really production. So it should put a really small overhead. It's actually a second use for a flight recorder is to record your own events, your logs. If you want to add some diagnostic logs and really want to have a small overhead on the logging, then you can also use this framework for your own events, and you can add them. Some people really do that. Okay, so we see nothing really special from that. I can tell you that in this particular case, Java Flight Recorder doesn't really help much, especially if we look into the graal. We see that not that much was recorded. Like graal almost haven't seen because it's using sampling and it calls for our code. And even worse, things like allocations look empty. So when I see such, I have seen such graphs, at first I thought maybe it's not working for graal. In fact, the problem is deeper, and we'll see that later. So, okay, Java Flight Recorder, it's really useful. I do recommend you to, if you haven't seen it, to check it. Maybe there will be a moment where you will need it. But now, here we go with a different tool. So what we have here is JPS. By the way, nothing special, just list all your Java tasks, all your Java processes in order to get you a process ID, PID. If you have it, you can use this tool, Jstack. What is a Jstack? Simply prints you stack trace of all stack traces of all threads of your program. Now, funny thing, why do I present this tool? Because a lot of times that was the only tool I had on a production because nothing else was installed. Because that was like a piece of code no one really thought will be, in fact, problematic or will be critical or something will happen. So this is the tool number one you have when you just on the server, production server and nothing is installed there, and you don't have any dumps, anything to analyze, but you have a running slow server and you want to check what's going on. Then you can use Jstack, which is basically dumps you stacks. So you do typically a couple of them, and then you see maybe that one of the stacks is really appearing a lot, and it's every time you dump, you see particle long stack trace with some methods. Some people even claim that this is their number one of finding and really solving issues for customers. That's like, if they could have one tool, this is the only one they need. I can also confirm that it's really, how to say, unexpectedly productive, unexpectedly efficient, although it has one small issue. I will explain later. But nevertheless, if you do it with a Jstack with Graal here, it also doesn't help much. It shows you something, but it seems that we are never in a particular piece of a code that should be slow here. But this is something. A problem of stack traces is save points, something called save point bias. I don't have time to describe it much, but basically Java doesn't stop. Normally, JVM doesn't stop on each line of code. If the piece of code you have is just heavily calculations without calling of other methods, IO or something, it was in the past, now it's actually a little bit better, but it was that JVM would never stop and would never report a stack trace from this point. It would actually wait till the method ends and think of like some heavy calculation that takes 1 second. Then you would have, with a sampling, results which are always, in fact, wrong, because we'll never see in a stack trace couple of lines of calculations, always some lines later. And all the also CPU sampling profilers have this problem mostly. But interesting fact is Java Flight Recorder has a very sophisticated way to avoid save point bias. And in new JVMs, this problem is less relevant. But OK, we have not yet seen why Graal is faster for immutable. Maybe we need to go to assembly. So your JVM typically has something like called Preassembly flag. If you use it, you will see that nothing is displayed because you also need some additional library that you have to put inside your JVM installation. But that will be printed in the console. You will know what to do with a Google. I will save your time here describing. That's just one sharded library. Different for Windows, different for Linux, different for Mac, that you have to put in the JVM. Also must be more or less compatible with architecture. And then you will have this. So that's a really nice picture for me. Finally, I see assembly. And this is a dump. Each time a method is compiled into assembly by a JIT, you will have a full assembly code of this method. Does it help? Not if this is with this ugly AT&T syntax. And this is something, it took me a longer time to find that there is a hidden flag. It wasn't really described anywhere, that you can change syntax to Intel. Oh, now it's fully readable. So awesome. Now I see where the problem is. OK, almost. So those flags are nice, but you will be bombarded by tens of thousands of lines that probably won't help you, even if you know assembly. So there is a better tool for that built called JITWatch. And JITWatch collects these logs and puts them into the browsable version, so you can simply see all the compiled method of your code, and you can click on them, and you can see the code inside. So it's what does it mean? It's still the assembly, but it's now easier to just browse your code and see what's going on. So I did it with JVM 8. I haven't seen anything suspicious, but let's go to the Graal. And now to the assembly code of a Graal. And I can tell you, it took some time. Actually, I have found what's going on, but to follow this process, it would be really too much time. But at the end, basically, what was really visible that the code of Immutable was almost perfectly simplified to just a loop and add in assembly in 20 lines of assembly. That was really awesome. But let's say we are not that proficient with assembly. This really takes a lot of time even for simple pieces of code. And I've never solved actual productive issue with reading assembly. This is a mostly tool if you are doing something and are interested what this compiler doing just for fun. And if you see that, for instance, a piece of code behaves way better or way worse if you upgraded JVM. But really, it's like you had the 8 version and now you have 8.240 something. And you see a difference then because code looks more or less the same. You will see probably what might have happened, and then you can probably read about the optimization. But if this is like version 8 and version 10, and you compare assembly, it's so different that any analysis makes no sense. So there's additional tool, command line tool, also usable, JStat, which in case you didn't enable GC-logs. And some people say you always have to enable garbage collector logs for your JVM. In case you didn't do that, you can do that later. You can connect to this JVM with a JStat. Again, you will have a pit of the process with JPS, and then you can see what's going on. And you will see how garbage collector works with this version Java 8. Okay, we see young generations adding old generations. Something is happening here. Well, we are creating tons of objects because we have immutable calculator. Well, what's happening in the graal? So the point, nothing. Here, garbage collector does nothing for all the time it's inside the measured method. And that exactly shows the optimization. So we don't create objects here. The code was really compiled by JIT to very efficient assembly, really. In fact, I have found it, and it's like how we would do that with C or other language. If you've written totally immutable, I think I haven't actually seen how immutable part of the code looks like, but would be the same, I think, assembly code at the end. Okay, there are, of course, lots of other tools like JProfiler, Dynatrace, especially if you have multiple servers. They are used commercially. They cost a little bit, especially Dynatrace if you use it, but I do say if you have a serious business, it makes sense. It saved me a lot of time. But it's also, even though I sometimes had those tools, I was using those simple ones, especially Jstack, JStat. And even, if you can analyze the code, then Preassembly, print inlining, all that stuff also might help a little bit. Okay, if we still have some time, so I will go quickly through some examples I've prepared, because that's were the tools I want, most important tools, like I would say, maybe not that commonly known, but now let's go deeper. Let's talk about monad transformers for a short time. So we have something like a user object, which has ID, parent ID, and we have a group of users. And we'll have a method. I wanted to create some example. The method that finds user, but returns a task because maybe it's lazy, maybe it's in a file, and option T. So basically, it's a task of option of T. So we used monad transformer for Scala Z, option T here. I hope I used it correctly. I'm not that proficient with Scala, and I'm not really using that monad transformers in production. So maybe here is error, but I think it should be more or less like this. And what we'll do, if we'll take indices from 1 to 100, we'll find users, and for these users, we'll find parents. Sometimes, because the data is constructed in a way, some users actually, for instance, refer to parent number 8. We don't have parents, so that's why here this option is. So maybe the user is not there, and maybe if the user is there, there will be no parent. So at the end, we should have a list of options, actually a task of options. And 3 of them should be, in fact, found. That's how I checked if the code is correct. Okay, so this is monad transformer solution that I will be analyzing, comparing to something. So to what? The first thing I thought, maybe let's compare it to stacked monads. So simply, let's do the same with a task option, but without strictly monad transformer, just stack a monad, task of option of user. That's here, so I had to write my own flat map. Actually, that was a pleasure, but nevertheless, I did it. So, and yeah, let's see what happened. So monad transformer versus simple stacked code on JVM 8. Monad transformer is indeed slow. It's not that slower, but compared to stacked monad, it's still something more happens. And if you look at the code, it's kind of obvious because in order to use monad transformer, I anyhow call a sum constructor from options, so it's kind of a stupid usage. So, but okay, let's compare it to something serious. To the best solution we know from Java, so null. Forget about task, forget about laziness. Just find user returns user or null. The same with parents, so now we don't need a flat map. It's so much easier to read if, else, of course. That's how people in Java were doing for years. Okay. So as you see here, null is so awesome. It's, not 10 times, but let's say 5 times faster than even stacked monads, and way better than monad transformers. I think if you take seriously all the benchmarks, you should start use null from right now, always, and forget about option. That's what you will do, of course. But okay, give it a little bit of time. In reality, rarely search in a list. Maybe we are calling a database. So we'll have a select. And here, again, this is a very simple imperative solution. We call it select statement. Actually, then we, again, will get sometimes null. If not null, then we'll look for this parent. So it's like ugly solution with database, but the simplest we can actually have here. Well, so now it's a picture that is really intriguing to me. So even though we used database as simple as possible, it's now actually only laughs from monad transformer stacks because it's so huge. We take so many nanoseconds to even do this couple of simple database queries, yes? That's something what you really do in reality. And even now, let's put what would be a database with monad transformer usage. So like clean way of using database with task on a row and monad transformer. If you look at this picture, if you already have database, this monad transformer is obviously on overhead. Is it that big? Depends, of course. But this is a picture that really shows what happens in reality. We talked a lot about monad transformers. The problem is in a different place. So maybe we even analyze this. And instead of doing, this calls, we used join to really find parents in one query. That would be this. So that's the lesson I have from the beginning when I started to do anything on production, that we sometimes really are, even for months, looking at the wrong place to fix the issue because we don't do a profiling, we don't concentrate on real problem, we remove. Okay, I have never actually experienced removing all monad transformers, but I've experienced removing, frameworks, EJBs, all that stuff that actually at the end, even though they were ugly, they were not actually having no impact on performance because the problem was in a different place. Not always a database. By the way, typically also people think that the problem is a database. Few times we were optimizing database, even though the problem was, for instance, in JSPs. Yeah, that was a very funny lesson. So, by the way, graal doesn't change much here. It's more or less the same thing. So monad transformer, and in this particular solution of monad transformer, doesn't show any improvement on graal. Maybe I did something wrong. Maybe graal did something wrong. Maybe that's how it should be. We can also go a little bit deeper in assembly in the next step. Okay, so one also important tool, if you are really interested into the performance and really want to go even deeper than assembly, let's look at a small for loop. We have two-dimensional array, and we'll just loop through this row by row and calculate some sum. What can be simpler than that? Can be the same with while. Looking at the bytecode, you know that while actually even transforms to the way more imperative, simpler code than for in Scala. So now it's the easiest as you can have imperative while loop over the array. And there here a little small change. What I really did is I switched, now I go columns. Not row by row, but column by column. What do you expect about performance of this? Maybe you attend some talks about the performance. So funny thing or not funny, I expect a lot of you know that. This is how you call JMH. And you add this parameter particular. You will see that for loop is a little bit, for instance, it takes a little bit more time than while. But that wasn't really interesting for me. But funny that really this while, which is done transposed, so column-wise, it's so much worse than a normal while. Why is that? So maybe you know this picture, actually the famous one, latest numbers, and maybe you know that actually the code always takes data from cache, never directly from memory. Let's say I'm talking about now about modern processors like AMD, Intel. It might change in the future. It wasn't like that 30 years ago, but we, developers as me, we still think in these categories of RAM, which each assembly code, I take a piece of information from RAM, etc. No, it's not like that. We take from packs. So if we access data not one by one, it means that a lot of time we're actually reading data that's not in the cache. And this can be measured. So if you use this performance counters with, for instance, JMH has a convenience for that you can display internal statistics of your processor that will show you a lot of interesting things. Like, for instance, how many times you missed the cache. And this is particularly example of this transposed column-wise while loop on an array, where almost 70% of our access to memory was a cache miss. So cache misses, a lot of them, as you see. This, on the other hand, if we compare it to the, let's say, regular solution that everyone would do, you see here, it's like quite a good, only 12%, okay, 13% cache misses. This is the, I would say, this is the case that it's quite often presented on talks about performance, about the CPU, how the things internally work. Like example number one, interesting thing is that some people from Intel claim that on the newer Intel processors, you sometimes wouldn't see this because now the out-of-order execution is is able to outsmart it. I have never seen that. The things that I've read, let's say, are not official Intel statements, so I cannot confirm that. Take it as an anecdote. But might be that one day, one of the guys will be presenting that you on the screen, and you will do this benchmark on your own, and you will actually not see the difference. This probably will happen sooner or later. So in this talk, I haven't covered garbage collectors, and those are very complex beasts, and few times I was able to totally destroy or fix performance of a production tuning or untuning garbage collector, just playing with that. Ahead of time compilations that you can create, let's say, native code, I haven't covered because it's not about making the code as performant as typically you would get code which performs worse on the long run. It just starts faster. The JVM options, actually, there are tons of them. I mentioned, for instance, that you can, for instance, improve inlining, improve that you will inline longer methods. Typically, it goes counterintuitive that you, whenever I try to fix something, make something better with JVM options, in the end, I get something that performs worse. I don't know why, it happens. That's why you do benchmarks and check all the time. So those benchmarks that I presented you and numbers were taken unprofessionally because that wasn't about benchmarks, about numbers, about monad transformers. All benchmarks are, lies because those are statistics. So if you are doing something because you want to do business decision based on the benchmarks, what is like when the benchmark is good? When you did it on your own, on your, let's say, your environment that you control, that you can check. When you read, you know the tools you tested. For instance, I would say maybe I did something wrong with monad transformers because I lack experience with that, with Scala Z. And finally, that's for me the most important part. When you see the difference, you try going even to assembly, to counters, see what's causing that. Finally, maybe you will see a line in release of JVM that this was fixed here, or release of your tool that they don't do that and this tool does it. Additionally, you need to know why something is faster or slower in order to do a really relevant decision, and then think, will that be in the future? Because maybe right now something doesn't behave great on a hardware, but will be good in a couple of years because hardware changes. The lessons I learned in the past, a lot of them are not relevant anymore. The times have changed. Yeah, like with this branch prediction. So, by the way, those are tools. I would say some of them were simply toys, and they do not really help that much in production. Although, let's say Jstack is particularly Jstack is really efficient, effective in that. In my real life, I had a couple of funny problems on productions. A lot of them not funny, but for instance, in a really dirty piece of code, we haven't seen that someone is reading tens of thousands of rows because the code was so hacky and so crazy that no one would even suspect that and wasn't visible. A lot of times I've seen something like a global lock. So you have 20 cores, but actually only one works. This is typically visible because CPU is idle. IO is not doing nothing and your application doesn't work. Really, it's easy to make this, and even seen sometimes cluster locks. Hash code bugs, more sophisticated when you put something, when you have a hash code on an object that actually changes. So you put something as a key to the map and you never get it back. Think about all the caches that you have then build a cache that actually never returns anything from it, and only it's your memory. It happens a lot in real life. This is very easy bug to make. Also I've seen JVM bugs. That's all. You have to, sometimes you just go and find that there is an issue in the particular version of JVM or you are using like metaspace. There were a lot of issues with metaspace and eaten memory and stuff like that. So a lot of these issues, again, I'm saying that because a few days ago I had talked with some guys doing this performance analysis, and they said, one of them said that he does confess that Jstack is his tool #1, and I have to say, yeah, might be. That's something. Okay, that's all I had for now. I'm open to questions. I will be later on a Zoom if you have any. This talk I published on a SlideShare, but I haven't shared you actually, so I will do it now. Okay, thank you.
Thank you, Jarek.